Dark matter simply explained. What is dark matter? Dark matter is invisible, undetectable stuff that makes up about 85% of the universe's mass. Unlike regular matter, it doesn't interact with light, making it impossible to see directly. Scientists know it exists because of its gravitational effects on visible matter. The concept of dark matter arose when astronomers noticed galaxies were rotating faster than they should based on their visible mass. Something unseen was providing extra gravity to hold these galaxies together. This mysterious substance was dubbed dark matter. Dark matter is fundamentally different from normal matter. It doesn't absorb, emit, or reflect light. It passes through regular matter without interacting, yet its gravitational influence shapes the structure of the entire universe. Evidence for dark matter. Galactic rotation curves provide the most compelling evidence for dark matter. Stars at the edges of galaxies orbit much faster than expected based on visible mass alone. Without dark matter, these galaxies would fly apart. In 1933, astronomer Fritz Zwicky first proposed dark matter when studying the Coma cluster of galaxies. He found the cluster's visible mass was far too low to account for the motion of its galaxies. Zwicky calculated that unseen matter must make up over 90% of the cluster's mass. Gravitational lensing offers another line of evidence. Massive objects bend light passing near them, acting like cosmic magnifying glasses. By measuring this bending, scientists can map dark matter distributions. The Bullet cluster, where two galaxy clusters collided, shows dark matter clearly separated from visible matter. The cosmic microwave background, leftover radiation from the early universe, also supports dark matter's existence. Its pattern matches predictions of a universe containing abundant dark matter. Composition theories. WIMPs. Weakly interacting massive particles are leading candidates for dark matter particles. These hypothetical particles would have mass, but interact very weakly with regular matter. Large underground detectors are searching for rare WIMP collisions with normal atoms. Axions offer another possibility. These ultralight particles were proposed to solve problems in quantum chromodynamics. If they exist, axions could make up dark matter. Experiments use powerful magnets to try converting axions into detectable photons. Machos, massive compact halo objects like black holes, neutron stars, and brown dwarfs were once considered dark matter candidates, but observations show there aren't enough of these objects to account for all dark matter. Some researchers propose modifying gravity laws instead of invoking dark matter. Modified Newtonian dynamics, MUND, suggests gravity behaves differently on galactic scales. However, most scientists favor dark matter explanations as they better fit observations across cosmic scales. Dark matter distribution. Dark matter forms vast cosmic webs with galaxies and galaxy clusters nestled in dense nodes. Computer simulations show how dark matter's gravity guided the formation of large-scale structures in the early universe. While dark matter permeates space, it's not evenly distributed. It clumps together in halos around galaxies and clusters. Our Milky Way sits within a massive dark matter halo extending far beyond the visible disk. Interestingly, some galaxies appear to contain little or no dark matter. The ultra-diffuse galaxy NGC 1052 DF2 shocked astronomers in 2018 when observations showed it lacked dark matter. Such outliers challenge our understanding of galaxy formation. Dark matter also forms smaller clumps called subhalos. These could range from dwarf galaxy size down to Earth mass objects. Detecting these small-scale structures could reveal dark matter's fundamental nature. The hunt for dark matter. Direct detection experiments aim to observe dark matter particles interacting with normal matter. Deep underground labs shield sensitive detectors from cosmic rays and other interference. Despite decades of searching, no conclusive signals have emerged. The Large Underground Xenon LUX experiment in South Dakota uses 370 kilograms of liquid xenon to search for WIMP collisions. Its successor, LUX Zeppelin, will be 30 times more sensitive. The Xenon 1T detector in Italy recently observed unexplained low-energy events that could potentially indicate dark matter. Indirect detection methods look for dark matter annihilation or decay products. When dark matter particles collide, they might produce detectable particles or radiation. Telescopes scan the skies for these signatures from regions with high dark matter density. The Alpha Magnetic Spectrometer aboard the International Space Station hunts for dark matter signatures in cosmic rays. It's detected an excess of positrons that could potentially come from dark matter annihilation. Particle accelerators like the Large Hadron Collider attempt to create dark matter in high-energy collisions. If successful, detectors would observe missing energy carried away by the invisible particles. So far, no definitive dark matter signals have been found. Dark matter in the early universe. In the first moments after the Big Bang, dark matter played a crucial role in cosmic evolution. Its gravity provided the initial seeds for structure formation. Dark matter began clumping together long before normal matter, creating gravitational wells for gas to fall into. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. This released the cosmic microwave background radiation we observe today. The CMB's subtle temperature variations reflect the distribution of matter, both dark and normal, at that early time. As the universe expanded, dark matter's gravity amplified tiny density fluctuations. Over billions of years, these grew into the cosmic web of filaments and voids we see today. Without dark matter, the universe would be far more uniform and lack large-scale structures. Dark matter also influenced the formation of the first stars and galaxies. Its gravitational wells allowed gas to condense and ignite fusion much earlier than in a universe without dark matter. This accelerated cosmic evolution and the reionization of the early universe. Alternative theories. While dark matter is the prevailing explanation for cosmic observations, some scientists explore alternative ideas. Modified gravity theories propose changing our understanding of gravity rather than invoking unseen matter. Modified Newtonian dynamics, suggests gravity behaves differently at very low accelerations typical in galaxies. This could explain galactic rotation curves without dark matter. However, Mond struggles to account for observations on larger cosmic scales. TeVe's tensor vector scalar gravity attempts to reconcile Mond with general relativity. It introduces new fields that modify gravity's behavior. While more comprehensive than MOND, TeVe's still faces challenges explaining all cosmic observations. Emergent gravity proposes that gravity isn't a fundamental force, but emerges from the quantum entanglement of space-time. This could potentially explain dark matter phenomena, but the theory is still in early development. Some researchers explore the idea that dark matter is actually an illusion caused by our assumptions about gravity across vast distances. However, most scientists consider dark matter the most plausible explanation given current evidence. Dark matter and galaxy formation. Dark matter halos act as gravitational scaffolds for galaxy formation. In the early universe, dark matter clumped together first, creating deep gravitational wells. Normal matter then fell into these wells, condensing to form stars and galaxies. Computer simulations show how dark matter guides cosmic structure formation. The Millennium simulation, completed in 2005, used over 10 billion particles to model dark matter's evolution. Its results closely match observed galaxy distributions. Dark matter halos continue shaping galaxies today. Their gravity influences star orbits and gas dynamics. Interactions between dark matter halos can trigger galaxy mergers and star formation bursts. Understanding these processes is crucial for explaining galactic evolution. Dwarf galaxies provide valuable insights into dark matter behavior. These small galaxies are dominated by dark matter, with visible matter making up less than 1% of their total mass. Studying dwarf galaxies helps constrain dark matter properties and distribution. The cuspy halo problem highlights a discrepancy between simulations and observations. Dark matter simulations predict dense cusps at galactic centers, but many observed galaxies show flatter density profiles. This mismatch challenges our understanding of dark matter dynamics. Dark matter in the Milky Way. Our Milky Way galaxy sits within a vast dark matter halo. This halo extends far beyond the visible disk, possibly up to 2 million light years in diameter. Its total mass is estimated at 2 trillion solar masses, with dark matter accounting for most of this. The dark matter halo influences the motion of stars and gas throughout the galaxy. It provides the extra gravity needed to explain the Milky Way's rotation curve. Without dark matter, stars in the outer regions would be flung into intergalactic space. Studying stellar streams, remnants of smaller galaxies consumed by the Milky Way, helps map our galaxy's dark matter distribution. These streams are stretched and distorted by the halo's gravity, revealing its shape and density. The Gaia Space Telescope is revolutionizing our understanding of the Milky Way structure. By precisely measuring the positions and velocities of billions of stars, Gaia allows scientists to refine models of our galaxy's dark matter halos. Some researchers propose that a dark disk of dark matter might exist within the Milky Way. This flattened structure could form from dark matter accreted during galactic mergers. If confirmed, it could have implications for dark matter detection experiments on Earth.